Assalamualaikum and a very good morning to Dr. Hakimah Binti Aziz and IR Dr. Sharin bin Ghani. My name is Muhammad Mujiril Akromin bin Hamzah and my supervisor is IR Alias bin Khamis. Today I will present my final project 2, which is modeling hybrid photovoltaic with battery in a standalone system. So this is the table of content for my presentation starting from chapter 1 until chapter 5. For introduction, solar energy is one of the most effective renewable energy sources and it can be used to power a standalone photovoltaic system for generating electricity in a remote region. SAPV with battery storage system provide continuous power to the load while store excess electrical energy. PV panel transfer power to the battery and load during daytime while battery to the load during nighttime. The problem statement listed are electricity grid is limited and not cost effective to be installed in remote areas. People in rural area of Sabah and Sarawak have difficulty in obtaining adequate electricity supply to cover the electricity consumption in these remote places. Therefore, SAPV systems are designed and built to electrify remote villages such as rural village, town or network of homes, normally located on an island or far from the closest power grid. There are three objectives in this project. Firstly, to design photovoltaic with battery in a standalone system by using MATLAB simulating software. Second one is to simulate and monitor the output of photovoltaic with battery in a standalone system by using MATLAB simulating software. Last but not least, to analyze the performance between photovoltaic system and battery storage system in the simulation of a standalone system. The scope of this project only focused for long house with capacity of 23 households. Next, the daily solar irradiance profile and module temperature with 1-minute interval are used, while the normalized load demand is with 15-minute interval. The design parameters of PV panel sizing and battery sizing are determined for energy consumption of long house at Long Bedian. Lastly, lithium-ion battery is selected as battery storage system. This is the summary of the literature review that has been done previously. The summary of literature review started with monocrystalline cell has been the most efficient type of solar cell with efficiency up to 70%. Next, standalone PV system with battery storage system is the most suitable solar system to be installed in a rural area. The design parameters of a standalone PV system are obtained in this chapter and will be used in chapter 3 to simulate the system design in MATLAB simulating. Last but not least, lithium-ion battery has been chosen because of its big charge capacity, fast charging and discharging capacity. This is the flowchart of the project that consists of data collection based on development of case study and actual profile for irradiance, module temperature and normalized load demand. Next, the calculation for PV panel sizing, battery sizing and daily power consumption demand are obtained by referring to the data collection. After that, the simulation is executed by using the parameter values that have been calculated and by using the actual profile data. If the simulation is not valid, so the process will refer to the calculation and execute the simulation again. If the simulation is valid, then can proceed for analyzing the result of solar irradiance, PV power, voltage and current, as well as battery voltage, battery current and the state of charge. This system consists of solar PV with MPPT, battery storage, DC load and AC load with inverter. PV panel will act as generation after receiving the solar irradiance from sunlight supplied to the battery and load. The maximum power point tracking block designed in the system is to detect the power condition of the photovoltaic panel to be supplied to the battery system. An MPPT controller will convert the input voltage to the correct voltage for charging the battery. Inverter is a converter that converts DC energy such as battery to be used by AC loads. Meanwhile, the controller tries to maintain the constant DC bus voltage in a varying load and solar generation scenario. This actual local load demand data is recorded for 7 months with 15-minute intervals. The daily peak demand for this load profile is 6 PM to 7 PM and start to decline steadily from midnight until 6 PM. The base load demand for the 23 household is around 8.2 kW, while the maximum load demand is around 18 kW, which occur on 7 PM in the evening. The load demand is changed from power, kilowatt, to resistance, ohm, in order to be plotted in signal video block that acts as an input to the variable resistor. The actual module temperature used in this project is for 3 consecutive days and recorded with 1-minute intervals. The temperature of PV modules impacts the system output and every type of PV panel have temperature coefficient that will affect the output of voltage and current. This is the typical use electrical appliances in rural or longhouse households. The result of calculation was demonstrated in this part consists of rural household power consumption, PV panel sizing, and battery sizing. The estimated load consumption is calculated by using equations 3.1 and 3.2 for a single household, which is 2 kWh. The selected location for this parameter design is Long Orang Longhouse, with 23 households that record the highest daily peak demand, while the lowest is recorded by Umar Bawang Longhouse. The load being used in the simulation is 46 kWh that represents the 23 households. The total PV use is 130 panels that has been calculated using equation 3.4 and 3.5, with sun peak hour value estimated is 2 hours by referring to the actual solar irradiance profile. This power generation from PV need to supply the 46 kWh load and charging the battery. Next, battery sizing was calculated using equation 3.6, 3.7 and 3.8. The 48 volt is set as the system voltage due to the big capacity installed in the system. Then, the state of charge is set at 30% because it is the inverse of that of discharge. The DOD for Long Orang Longhouse is 70%, so the battery bank required for this longhouse is 48 volt with 4900 ampere-hour. For the simulation design, it is divided into 3 parts, which are photovoltaic system with MPPT, battery storage system, and load design with inverter. The sizing of PV panel determined previously has been set at PV module. The PV panels get input from actual profile of irradiance and module temperature. For the photovoltaic system design shown in figure 6, advanced power API P230 is selected with maximum power Pmax of 230.124 watts. It is controlled by the MPPT to manage the PV panel performance because it boosts the efficiency of a solar panel by monitoring the maximum power point to be extracted to battery part. The output extracted is irradiance, PV current, PV voltage, and PV power. For battery storage system, lithium-ion has been selected due to its high performance. The system voltage, or known as DC bus voltage, is set at 48 volt. Blocks of VREF and VBus are used to control the input for IBREF. That will be the reference for charging and discharging of the battery from PV panels to the loads required. Meanwhile, the function of SP and SN blocks are to control the gate for positive and negative terminal of the battery that will also affect the charging and discharging process. The value of PID controller has been tuned automatically to get the best performance of charging and discharging process. The AC load is designed by using actual load profile data. Resistance values is used to be plotted in signal bidder block as an input to the variable resistor block. The inverter used is from online sources and just plug into the system. The performance analysis of photovoltaic and battery is based on 3 types of irradiant data, namely model A, B, and C, which consists of 3 consecutive days in year 2014 from 31 May until 2 June 2014, as shown in figure 9. Okay, here come the result and discussion part. Figure 10 shows the output waveform consists of solar irradiance, PV current, PV voltage, and PV power that has been taken into account for performance analysis of model A, B, and C. The simulation is run for 24 seconds, which shows the real 24 hours time. At around 2 PM, the irradiance profile suddenly dropped from peak value to below 200 watt per meter squares, and it happened about 30 to 40 minutes. The maximum PV power is obtained at 1 PM with a recorded value of 16,933 watt, and the highest irradiance value recorded is 977 watt per meter square. As irradiance increase, the value of voltage, current, and power of PV will proportionally increase. At peak irradiance, the PV power will also achieve its peak value. This is the output result for model B. At around 12:30 PM, the value of irradiance suddenly drops from above 1000 watt per meter square to below 100 watt per meter square, and it happened about 30 minutes. And once again, the value drops at 3:30 PM, but this time it is between 100 to 200 watt per meter square. The amounts of irradiance produced by the PV panel depends on the exposure of panel itself to the sunlight. At 1 PM, the value of PV power dropped significantly to 1776 watts due to sudden drop of irradiance value at 157 watt per meter square, maybe due to the local bad weather. The power PV and irradiance reached the best performance of PV at 4 PM. For model C, at around 11:50 am, the value of solar irradiance suddenly drops below 250 watt per meter square, and it happened about 50 minutes, and once again, the value drops at 12:45 pm, but this time it's between 300 and 400 watt per meter square. The best performance for PV system at 1 pm with PV panel generates more than 10,000 watts with a radiant value of 683 watt per meter square. At 1 am, the lowest PV performance are recorded where it produced only 51.34 watts since it is midnight. Figure 13 shows the battery voltage, battery current and state of charge of model A. There are 5 phases for the state of charge, starting from discharging, charging and discharging back due to the low irradiance at that time, and started to charging back for about 30 minutes before discharging as the night time comes. The battery having a discharge operation start from 7 pm until 7 am, while charging operation of battery occurred from 10 am until 4 pm. 0.0026% of state of charge values drop from 1 am until 10 am when the battery in discharging mode, but increase back when battery starts charging. For model B, there are also 5 phases for the state of charge. The battery current proves at 1 pm, where the discharging process happened only for a certain moment between 10 am and 4 pm due to engaging of battery current value for supplying the load. According to the output waveform, discharge mode occurs at night and charging mode occurs during the day. The battery starts to charge at 10 am but drops drastically at 1 pm with battery current of 42.18 ampere due to lower irradiance and high battery current. The value of battery current is negative when the battery is in charging mode. From waveform of state of charge in figure 14, it can be seen there is slightly discharging process during the charging mode around 11 am, maybe due to the few moments of cloudy weather, and it can be proved by observing a little lower of irradiance profile around that time. The battery storage starts storing energy at 29.9969% of state of charge, and SOC rises by 0.0070% during charging. The voltage difference between the discharge and charge states is just 0.02 volt because the voltage keeps constant. The result reveals the charging mode fluctuates in the negative zone of battery current as it is influenced by the input of solar irradiance. The performance analysis of PV has been done by observing and analyzing the output current, voltage and power from PV system. Meanwhile, performance analysis of battery has been done by observing and analyzing the output current, voltage and state of charge from battery system. The values and performance of the PV system has been greatly influenced by the value of solar irradiance data. Battery current values are inversely proportional to the battery voltage. As the RAD increase, the battery current will decrease to negative value and resulting the state of charge to increase, which initiates the charging process. Battery will automatically change from charge to discharge for supplying the energy to the load when the night time or cloudy weather. Last but not least, battery will change to the charge mode when the PV panel receives input from solar irradiance. In conclusion, the objective 1, which is design the photovoltaic with battery in a standalone system, was successfully done by using MATLAB simulating software. For second objective, the simulation was successfully simulated and output of photovoltaic with battery being monitored in a standalone system by using MATLAB simulating software. Lastly, objective 3 has been successfully done by analyzing the performance between photovoltaic system and battery storage system in the simulation of a standalone system. For recommendations, installation of solar panels in shaded areas must be avoided. Secondly, the battery connection need to be included by the arrangement of series and parallel in order to be applied in real site location. Third one, more models of solar irradiance and load demand profile need to be simulated in order to observe which parameters is critical and need to be focused on in designing the system. Last but not least, we can use other controllers to improve the voltage and current performance of the battery and PV panel. So this is the timeline or the Gantt chart for my project, which consists of FYP1 and FYP2. And I think that's all from me. Thank you everyone.